Hey everybody, Mr. Brooks here again for our last section in chapter 4. So this is 4.9, numerical methods for systems of differential equations. So this one is truncated down quite significantly. We are not going to do the Runge-Kutta method. You can explore that on your own if you will. So there's pretty cool things that come with that. But we are going to focus mostly on a type of numerical approximation method that we talked about in 210, which is Euler's method. So in section 210, we introduced it. So that's what's pretty much missing for all the blanks. We introduced Euler's method. All right. It was a numerical algorithm for approximating solutions of equations for the form y prime is equal to f of t of y. Now this again is dealing with scalar functions when we were dealing with those guys. So that's why we have this f of t of y, where we have some initial value and t is on a strictly closed interval. All right. So what we're going to do is we're actually going to extend this idea, and it's not much of a push for this extension onto a system of linear equations because of the things that we're allowed to do with matrices. We are allowed to take derivatives of the individual terms. We're allowed to take limits. So everything we need is already been established for us. So this push to make it fit for first order systems is really not much of a push at all. So just a recap of what it is. So a refresher on Euler's method. All right. So once we're dealing with this particular function, f of t of y, so again, I'm talking about the scalar version, we choose some step size h, and we approximate the solution of y at a series of equally spaced points, and we're going to call them here t1 is equal to t sub 0 plus h, t sub 2 is equal to t sub 0 plus 2h, and so on up to t sub n is equal to t sub 0 plus nh. All right, or another way to do that is we're recursively defining this. So here t2 is t1 plus h for that case. And so we will use y sub I to denote the approximation at t sub I. So y of t sub I is equal to, or approximately equal to, the function value y sub I. The approximate value of the solution is y sub I plus 1 is equal to y sub I plus h times f of t sub I y sub I. So what we're doing is making this approximate value in steps. And so this is a linearization technique of y. Okay, so this is where this is coming from. So again, this is where our refresher. So we're going to do that step-by-step method with the next piece. Okay, so extending Euler's method to first order systems. So here's our first order system. Y prime is equal to p sub t times y sub t plus g of t. Notice that I have bolded these letters, meaning that these are now dealing with the system. These are matrices or vectors of some sort. So here we're going to assume t sub I are uniformly spaced. So how we're going to do that is t sub I plus 1 is equal to t sub I plus h. So again, just like before. Or another way to state that is t sub I is equal to t sub 0 plus ih. Okay, and here I is some value between 0 and big N. And big N is equal to the number of steps. that we're going to be taking to get to our value. Okay, and that's all going to be dependent on h. H is going to be the driving force of how many of these are. All right, so the nice thing is if we use limits on y sub I, we can get our limit definition for y prime. We can find out, we get this approximation of what y prime is. So again, so using limit definition of the derivative for y prime, we find y prime is equal to 1 over h times y of t plus h minus y of t. This is approximately equal to our p of t, y of t, plus g of t. Now again, this is for very small values of h that this is true. Okay, so again, using that limit process where we're going for this. All right, thus, y of t sub I plus h is approximately equal, so if we solve this, is approximately equal to y of t sub I plus h times our p sub t sub I, y sub t sub I, plus g of t sub I. Since we stated before, since y of t sub I is approximately equal to y sub I, then y sub t sub I plus h is equal to, or approximately equal to, y of I plus 1. So this is our first iteration, so y sub I plus 1 is where that's coming from. So we can truncate this down saying y sub I plus 1, our next value is equal to y sub I plus h times p sub t sub I, y sub I, so the previous value, these are these previous values or initial values, plus g of t sub I. Again, we're using the previous values in this linearization technique on this system. So no better way to do this than to look at a particular example. All right, and I'm just going to do one example because this is a very straightforward process. There's not much with this section, so that's the nice piece. Especially since we are limited to just Euler's method, so there's not a lot going on with it. But I'm going to go through several steps with this one to show you the process. Again, it's going to be a little bit mind-numbing, but we can handle this. All right, so let's assume that our system here is one, so our piece of t, that's what this guy is, and this is our g of t. These are our initial values, so this is our IVP that we're dealing with. I want to use Euler's method to approximate y of 1.02 with a step size of 0.01. All right, notice we're given the initial value at 1, so we're going to have to do this 3 times. Okay, so we're going to have to find 1.1, 1.2 for our approximate values. Okay, all right, so here's our solution. All right, so y sub 0 is equal to 2, 1. T sub 0 is equal to 1. So now we need to find out what y1 is. Well, y1 is equal to y sub 0 plus h times p of t sub 0, y sub 0, plus g of t sub 0. All right, so how this looks? Well, y1 is then equal to y sub 0, which we said is the vector here of 2, 1, plus 0.01 times our our P of t of 0, so I'm going to write this one out. This is 1 t sub 0, 2 plus t sub 0, 2. So I'm going to do this one more step with this one. Y sub 0, which was 2, 1, plus g of t sub 0, which is 1 t sub 0. Okay, so a couple more steps with this. So this is 2, 1, plus 0.01. And now we can start cooking here. So our t sub 0 was 1. So we're going to 1, 1, 3, 2. Multiplied by the vector matrix 1, 2, or sorry, 2, 1, plus 1, 1. So now here we go. All right, 0.01. And then when we multiply this 2 by 2 by a 2 by 1, we're going to get a 2 by 1 back out of it. So this row times this column, so we're going to get 2 plus 1. So we're going to get 3. 6 plus 2 is 8. We're going to add this vector to it, 1, 1. So we get 2, 1 plus 0.01 times 4, 9, which gives us 2, 1 plus 0.04 and 0.09. So therefore, y1 is equal to 2.04 and 1.09. So now we're going to use that for our next iteration. Okay, so our next step is when t1 is equal to t sub 0 plus h. So that's 1 plus, so I'm going to put a line here, plus 0.01. So we're now looking at the value at t is equal to 1.01. This is an approximate value. All right, so I'm going to do this one in red so it's color-coded a little bit. So that means y2, because that's our next value, we just found y1, so we're finding y2 now, is equal to y1 plus h, p of t1, y1, plus g of t of 1. All right, y1 we found out was 2.04, 1.09, plus h, which is 0.01, times our piece of t of 1, which in this case is going to be 1, 1.01, 3.01, and 2. Again, because t now is 1.01. And then we have 2.04 and 1.09. And then we're going to add g of t of 1, which is 1 and 1.01. All right. So 2.04, 1.09. And we're going to add, and so I went ahead and did this one. We're going to add 0.0414 and just got to double check my math real quick. .0933. So in the end, we found out y2 is equal to 2.0814, 1.1833. Okay. Now we're ready to move on to our last value, t2. The reason I know that we're stopping there is because this is t1 plus h, which is 1.01 plus 0.01, and we are getting to the value that we want. We want to know what happens when it's evaluated at 1.02. So y3 is equal to 2.0814, 1.1833 plus 0.01 times our new piece of t, which is 1.02, 3.022 times our y sub 2, which was 2.0814, 1.1833 plus our g of t, which is 1 and 1.02. All right. So we got 2.0814, 1.1833. All right, so when we multiply these two together, we are going to get 3.28836 and 8.652428 plus 1.02. And then we're going to multiply that by 1/100th. So we are going to get 2.0814, 1.1833 plus the following horrible number, 0.0428836 and 0.0967248. Adding these guys together, our approximate value at t is equal to 1.02 is 2.1242836 and 1.28002428. And that's how you do this. So again, a lot by hand to get there, but these guys are not that bad. It's very, very similar to our process, and it's actually pretty much a straightforward analogy to scalar. We're just now extending it out to matrices. So this is the nice thing, is the process maintains for the whole entire thing. And so that's when we know we stop, is when we reach t is equal to 1.02. All right, so that's it for today. And that's all I have for you guys. So this will end chapter 4. We only have 2 more sections left for the end of the semester, because we've truncated down to just 6.2 and 6.4. And then we'll be done. And we'll have a review and several review days for the final. Y'all have a wonderful day.